to my today's session on Ampere Circuital Law. Myself, Dr. Sayanti Chatterjee, Associate Professor of Institute of Aeronautical Engineering College, IARE, in Electrical and Electronics Department. Today I will discuss about the Ampere Circuital Law. Ampere Circuital Law is analogous to the Gauss law in the electromagnetism. What is Ampere's law? So before Ampere Circuital Law, we will discuss about the Ampere's law. According to the Ampere's law, magnetic fields are related to electric current produced them. When current flows through any coil, it creates some field. According to the Ampere's law, magnetic fields are related to the electric current produced in them. The law specifies that the magnetic field that is associated with a given current and vice versa, provided the electric field doesn't change with time. This law specifies that if for a given current one magnetic field has been generated, or due to any magnetic field, if any amount of current is generated, the electric field due to this current doesn't change with the time. And this is known as the Ampere's law. And using the Ampere first given the law on current, that's why the unit of current is taken as Ampere. So in the language we can tell the magnetic field created by an electric current is proportional to the size of the electric current with a constant of proportionality equal to the permeability of the free space. So the magnetic field created by an electric current, if the current flows through any ferromagnetic material, it will change into magnet and it will create some magnetic field. So magnetic field created by an electric current is proportional to the size of that electric current with a constant of proportionality equal to the permeability of the free space. Now we will move to the Ampere Circuital Law. Ampere Circuital Law is same as the Gauss law in electrostatic field. Ampere Circuital Law can be written as the line integral of the magnetic field surrounding closed loop equals to the number of times the algebraic sum of current passing through the loops. Means if there is a magnetic field surrounding a closed loop, is the amount of the magnetic field, the line integral of the magnetic field equal to the summation of the algebraic sum of the currents passing through the loops. I am giving one example. So see, we have a loop like a square wave. So the magnetic field, the integral of the magnetic field in this closed loop is the summation of the current, the summation algebraic sum of the currents passing through the loop, means current passing through AB, BC, CD and DA. If this is I1, I2, I3 and I4. So like this, the addition, summation, and this is the line integral of the magnetic field. Suppose a conductor carries a current I, then the current flow generates a magnetic field which can be written as this integral means closed loop path. The integral in a closed loop path H dot dl. The equation's left side describes that if any imaginary path encircles the wire and the magnetic field is added at every point, then it is numerically equal to the encircled by the root and it is written by the I enclosed. The equations of the left side means H dot dl, that is an imaginary path. Practically we cannot see the magnetic lines of force. So this is the imaginary path encircles a wire if there is a cross conductor, if this is the magnetic path and this magnetic path is the imaginary in nature, encircles the wire, the magnet field is added at every point, then it is numerically equal to the H dot dl is equal to I enclosed. So Ampere Circuital law can, as I discussed earlier, if we want to check in the top view and the side view or front view, we can tell the line integral of a magnetic field surrounding closed loop equals to the number of times the algebraic sum of current passing through the loops. Line integral of H dot dl is equal to I enclosed. So if this is a conductor, current I is flowing, it has some axis x, y, z. This is the top or side view. If we think the current, now if we check this current is flowing through this, the field will encircle. This is the imaginary line of the circulating wire. So what are the applications of the Ampere Circuital law? The first and foremost application is the magnetic field intensity in the surrounding closed path always at the tangential at each point and every point on it. So what does it mean? In this circle, the direction of the magnetic field, is always tangential on each and every point. The direction of the magnetic field intensity H is always the tangential on it. So first point is clear, I think. First point, the magnetic field intensity in the surrounding closed path is always at the tangential at each and every point on it. At each and every point on the closed path, magnetic field intensity has the same value in every point. In one circle, if we are taking a circle of r diameter, in each and every point, the H value is always same. Determine the magnetic induction. So what are the applications? Application first is that we can determine the magnetic induction due to long current carrying wire. So what is the formula? Integration of HDL is equal to I enclosed. We can calculate the magnetic field of a toroid. As I discussed in my previous lectures, what is the meaning of the toroid and solenoid? Solenoid means a bar on which the conductors are mounted, and these two are the two open paths. What is the meaning of the toroid? Toroid means the circular or disc-like paths on which we can find the conductors and the two ends are always connected. Determine the magnetic field for a long current carrying cylinder. If we think about a cable is not a wire, cable is a cylinder. It has a certain radius, so we can calculate the electric magnetic field using the Ampere Circuital law. Next one is the determine the magnetic field inside a conductor and find forces between current carrying conductor. So these are the procedure of the Ampere Circuital law. So first we will discuss the Ampere Circuital law for a long current carrying conductor. From the Ampere Circuital law, we know that the integration of HDL is equal to I. But we can also write as the integration of the JDS is equal to I. What is J? J is nothing but the current density, and we know that J is equal to di by ds. So integration of J ds is equal to di. Integration of di or I is equal to integration of J ds. So if we equal these two equations, we can write integration of HDL equals to J ds. Now this side dl, this side ds, how we can make it the equal? Because if we want to equate two equations, then we both the line should be in the both the line should both the integral variable will be in the same standard. So one is dl and one is ds. So we can use the Stokes theorem. H integration of h dl can be written as the grad cross h ds. So we can write, by combining these two equations, we can write grad cross h ds is equal to j ds. So grad cross h is equal to j. Grad cross h is known as the curl of h, and grad cross h is equal to j is known as the Maxwell's third equation. And h dot dl, grad cross h ds, is known as the, this is the point form, and this is the integral form of Maxwell's equation. This is the integral form of Maxwell's equation. This is the point form of Maxwell's third equation. So as I told, this is known as the integral and form of Ampere's law and calls as the Maxwell's third equation. The another name of this equation is the Ampere Circuital law in the vector form. So how we can write? We can write integral. Actually, it is the circular path integral h dot dl is equal to I enclosed. Again, we know that integration of j ds, j is the current density, is equal to I. So if we equate the both sides, we will get h dot dl is equal to j dot ds. Now this is the dl and ds, so we can write grad cross h ds is equal to j ds. And if we equate the both sides, we can write grad cross j is equal to, so grad cross h is equal to curl of h. Now we will discuss the Ampere Circuital law for a circular conductor. Let us consider a straight line conductor as shown in the figure. And it has been surrounded by a radius circle of radius r. So according to the Ampere Circuital law, we can write h dot dl is equal to I. So integration of h dot dl, h is a constant as I discussed in the previous properties of the Ampere Circuital law, that the h at each point is fixed. So h dot integration of dl, so h is equal to constant, so h integration of dl. So if the radius is r, we can write as h 2 pi r, and from the Ampere Circuital law things, h 2 pi r is equal to I. So h is equal to I by 2 per h is equal to I by 2 pi r. This is the Ampere Circuital law for a circular conductor, means the conductor is in a circular format. Next we will discuss about the Ampere law for a square conductor. Ampere law for a square conductor. This is a square conductor, and on which we can mount the conductors. So each side we have taken as the D. Each side is taken as the D. This is the AB, BC, CD. So AB is equal to BC is equal to CD is equal to DA is equal to D. So let us consider a square sheet as shown above with surrounding path of side D. According to the Ampere Circuital law, integration of h dl is equal to I. And now from the previous one, you can see that if this is the L, if it is as this is a square, so integration of dl is equal to 4d, because d plus d plus d plus d. So it is the integration of dl is equal to 4d. So h is equal to I and h is equal to I by 4d. Now we will discuss the Biot-Savart's law. Ampere Circuital law and Biot-Savart's law are connected together. What is Biot-Savart's law? The magnetic field intensity due to the current element IDL is dH at point P. According to the Biot-Savart's law, dH is directly proportional to the IDL. So if it is a current carrying conductor, we are calculating at a point P, current is flowing is IDL, we can write that the field intensity at point P, dH is directly proportional to the IDL. We can also write that dH is directly proportional to the sine theta. What is sine theta? Sine theta is the angle between current element and length joining the point. dH is also directly proportional to 1 by r square, square of the distance between current element and point. So if we adjust this 3, it will be combining this 3 means dH is directly proportional to IDL sine theta by r square. So by removing the proportionality, we can write dH is equal to IDL sine theta by 4 pi r square, and this is the total magnetic field intensity. Total magnetic field intensity at the point P. Now what is the relation between dB and dH? We know dB is equal to mu into dH. So we can write also B equals to mu. Okay, first H is equal to integration of IDL sine theta by 4 pi r square. So what is B? B is nothing but the mu IDL sine theta by 4 pi r square. As I told, B is equal to mu H. Now, if we want to write it in the vector form, what will be the change? So we got H is equal to integration of IDL sine theta by 4 pi r square. Therefore, the total flux density at point P, B is equal to mu H, and B is equal to integration of IDL sine theta by 4 pi r square. Now, what is the meaning of the, and this is one mu. So, what is the meaning of the dl sine theta? We know if we take A cross B is equal to AB sine theta. A cross B equals to AB sine theta. So, here we got dl sine theta, and dl we can write dl into 1 dl into 1 into sine theta. We can write like this. So dl into 1 is nothing but the unit vector. 1 is nothing but the unit vector. So we can write dl in the another vector is ar cross. So dl cross ar is the same like dl1 sine theta. Ar is the unit vector along the radius. So dl sine theta can be written as the dl cross ar. So h can be written as I dl cross ar by 4 pi r square, and this is the vector form of the Biot-Savart's law. So from the vector form of Biot-Savart's law, we got h is equal to I dl cross ar by 4 pi r square. Now, using Biot-Savart's law, find the expression of the magnetic field intensity due to a long current carrying conductor. Already in my previous lectures on Biot-Savart's law, I have discussed in details. Here just we will discuss in a small way. So see, we have a very long conductor whose length is dl. So current flowing through it is the ideal. The point is here 0, 0, z. Because as this is a conductor, we will take it as a cylinder. So it is the 0, 0, z, and this is like the flux will come like cylindrical. So we are taking one point P whose intensity we have to calculate, and its value we are taking R 0, 0. So if we want to calculate the distance between the P and the line, P and the conductor, we know the line equation means end point minus starting point. End point minus starting point. So end point is R, A, R. Starting point is Z, A, Z. Because we are taking the R, phi, Z. The cylindrical components of R, phi, Z. So it will come R, A, R minus Z, A, Z. And what is R? R is equal to, if this is the length is Z, this is the small r, D is equal to small r. So capital R, the distance between the P from the end of the conductor is root of R square plus Z square. Root of R square plus Z square. So what is R by R? R by R is AR, as we discussed earlier, that the R by R is equal to AR, the unit vector. So now we have to calculate H is equal to I dl cross AR by 4 pi R. What is dl? dl is Z, A, Z. We have the 3 unit vector AR, A phi, A Z. We have 3 unit vectors. AR, A phi, A Z. AR, A phi, A Z. So first we will take DL. DL means 0, 0, dz. And what is the equation of the AR? AR is equal to minus Z plus R. Phi is 0. So if we multiply it, we will get the RZ A phi. If we calculate the cross product, we will get RZ A phi. So this equation can be changed into I R dz A phi by 4 pi R square. Now how to solve this equation? Let's check. Z is equal to R tan theta. So Z is equal to R tan theta means dz is equal to R tan theta differentiation of tan theta is equal to R sec square theta. So we put the and Z square is equal to R square tan square theta. If R is equal to tan theta, Z square is equal to R tan square theta. So for an infinity conductor, Z length is equal to minus infinity, and minus infinity means minus infinity is equal to R tan theta. So theta is nothing but the minus pi by 2. And Z is equal to plus infinity is equal to theta plus pi by 2. So here we can change the equation. Here we can change the equation. R in the place of dz we can write R sec square theta A phi. A phi is only for the direction, so no need to take the A phi in the time of integration, by 4 pi R square. What is R square? Z square. We got the 4 pi R square. So if we put it, we will get minus infinity to plus infinity I by 4 pi R. What is dz? Dz is nothing but the R sec square theta divided by R square. Because R dz. So if we put the value, we will get that H is equal to I by 2 pi r and direction is in the Fi direction. And if this is the intensity for a long current conductor, if the distance is the finite distance, there is a small change. If Z is equal to A, phi is equal to tan alpha. And what is alpha? Alpha is nothing but the tan inverse R by A. Or we can write like this. Z is equal to A R tan theta. So theta is equal to tan inverse A by R. We are writing this angle alpha. Similarly, if Z is equal to beta, we can write the equation as the tan alpha beta, and the equation will change as I by 4 pi r sin alpha minus sin beta. Now one small problem we will discuss now. A current of 1 ampere is flowing in a circular coil of 10 cm and 20 tons. Calculate the intensity of the magnetic field at a distance of 10 cm on the axis of the coil and at the center. So magnetic field at the center H is equal to I by 2R. For a circular coil with number of turns n, so we can write Ni by 2R. So N is equal to 20 turns. I current is equal to 1 ampere by 2R, 2 into 0.1. So the value is coming 1000. Remember the unit 100 ampere turn per meter. If we want to calculate at a distance r, the formula is Ni r square by 2 r square plus z square 3 by 2. N value we know, I value is actually I value will come 1 ampere. One small mistake. Into r square is 0.01 by 2 r square by z square. So if we solve it, we can get the value of n. Okay. And it will be the 35.35 ampere turn per meter because it is the 1 ampere. Extract the expression for the Maxwell's second equation. From the Gauss law, we can write the Maxwell's second equation in the integral of the magnetic flux density. So psi is equal to B dot ds. But the total flux density in the closed surface is always 0. So we can write psi is equal to B dot ds equals to 0. So B dot ds is equal to grad dot B dv is equal to 0. So this is the Maxwell's second equation. So in the today's lecture, we have discussed about the Ampere's law, applications of the Ampere Circuital law. Then we have discussed about some equations of the Biot-Savart's law, the applications of the Biot-Savart's law and the equations. And this is my today's class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.